We need to start with the Pascal law, which is very simple, that pressure inserted by the liquid will remain the same in all directions, and it will be perpendicular to the container or to the vessel that carrying the fluids. So one question arises here, that why we always use the circular pipes for hydraulics or for conducting the fluid? Why not rectangle, triangle, or any other cross section? So the reason is that only the circular cross sections are having maximum surface area. So in hydraulics, we are interested to increase the surface area, because with the surface, or I would say increase the cross-sectional area, so which in turn increase the capacity of that pipe, of that conduit to carry the fluid. So for example, just for example, if we talk about the 3-inch pipe, so keeping a velocity at 1.5 meter per second, the maximum water carrying capacity of that pipe is around 28,000 liters per hour. So if we go for 3-inch rectangle or 3-inch triangle, the carrying capacity will reduce. So what we are interested in always in, because we just want to have a lower dia for higher flow to economize our projects. So that's why the circular cross section or the circular shape carries the maximum surface area and in turn the cross section area. So that's why we prefer, we go for the circular areas rather than any other cross section areas. Continuity law, it's very simple, that amount of fluid entering here will remain the same regardless the cross section area. Whatever fluid enter here, for example, from here we have a flow of 10 cubic meter per hour. So from the A2, or from the outlet of that conduit, it must be 10 cubic meter per hour, regardless of the area, either it's higher or it's low, it's matterless. So this is continuity law, that the amount of fluid flowing in the conduit, if there is no outlet, and even if there is only a single outlet, so the amount of flow entering the conduit will remain the same that leave that conduit. So you see here the area A1 is higher or larger than the area A2. So in turn the fluid will manage itself in a way that it has to increase the velocity. It has to increase its velocity by itself. It's a natural phenomena just to maintain the total flow rates. So if A1 is greater than A2 and flow remains the same, V1 must be less than V2. Velocity at higher cross section must be lower than the velocity at smaller cross section area. So that is all about the continuity law. Bernoulli. So these three laws basically we applied in hydraulics, so that's why we are just mentioning here. What Bernoulli actually, it expressed the law of conservation of energy in fluids or in hydraulics. What it said, the energy can neither be created nor be destroyed. Whatever the energy you are giving to the fluid, it will remain the same. It may change its shapes, it may change its form, but the total energy remains the same. And also, in other words, it says that if there is increase in velocity, there must be decrease in pressure. So the product of V and the product of P, velocity and pressure, it remains the same. So if either of it is increasing, the other will have to decrease by the same proportion. You must have seen these graphs in your textbook. Just mentioning here that if we have a simple tube installed at the pipe, the water will raise to certain height. That height will call hydraulic grade line. But if you have a petard tube like that, water will raise to a level slightly higher than the one in a simple tube, because now it includes the velocity head as well. So the sum of these two, hydraulic grade line or the hydrostatic pressure along with the velocity head, which is V square or 2G, it becomes the energy grade line. But what about the total energy line is, that line remains the same from this start to the end as mentioned here. The total energy line will remain the same but it, as I mentioned earlier, that it may change its shapes. So how? From here, it's a simple tube, the water rises to that level. With a petard tube, it rises higher to the hydrostatic pressure, so the difference will be velocity head. Because it is due to this shape, that petard tube shape, it also is measuring the velocity of that fluid. So it's a little higher. Now, in this pipe, right from here up to that point, for example, when there is a flow of liquid in a conduit, there must be friction losses. There must be some energy losses. It's very simple that if I'm traveling from that point to the farmost point, I must have to utilize some energies of mine. Or in simple words, if you are climbing up the hill, so after a little time you will feel exhausted because you are consuming your energies. So similar here, the fluid has to insert some energies in order to flow that fluid from that point 0 to some point, for example, up to that point. So during that travel, it will lose its energy, and that energy is called friction losses. So the total energy line will include hydrostatic pressure, velocity head, and pressure losses. Now, if you are going for a bigger dia of the pipe, the friction losses will reduce, the velocity will also reduce, but the hydrostatic pressure will increase. So whatever, and we call it total energy line, and the total energy line always remain the same. So, and it depends upon your design that whichever part will be higher. Either it will be velocity head will be higher, or the static pressure will be higher, or the friction losses will be higher. It also depends upon your design. For example, if you all are familiar with the rain guns or with the sprinklers, what we are doing is that up to the nozzle, we want to increase the hydrostatic pressure and reduce the velocity head. But immediately at the entrance of the nozzle, what we are doing is, or what we want the nozzle to do is, that to increase the velocity head. Because with the velocity head, now it has to travel from nozzle up to some other point like 100 feet, 50 feet, 150 feet, or even 170 and even 200 feet. So the moment the water left the nozzle, it has a velocity head now. It don't have any hydrostatic or friction losses, all will become zero. Only what it has is the velocity head, and that velocity will enable it to travel up to 50 to 100 or 200 feet. So that's how the pressure or the total energy lines converts its shape from one form to another form. That is the pressure nomination. For example, if we have 0 atmosphere, now standing in this room, we are being under the pressure of atmosphere, what we call 1 atmosphere. But it remains at the sea level. As you raise it from the sea level, the pressure decreases. And by the way, 0 atmosphere is not possible, because you will create 0 atmosphere with a vacuum pumps or with some other arrangements. So nothing is 100% efficient. So you can't avail the 100% vacuum. So absolute zero or absolute zero vacuum is not possible. But we are just taking it theoretically. If that is the absolute zero for the vacuum pressure, so that is the line for atmospheric pressure. And if I install a pump with a pipe and run the system, the pressure within the pipe will be the sum of atmospheric pressure along with the gauge pressure that is arising due to the installation of pump or any other arrangement. So the pressure at the gauge plus atmospheric pressure will become absolute pressure. And if you decrease the pressure in the piping network due to with any arrangement, basically you are creating a negative pressure, so we call it a vacuum. But 100% vacuum is not possible.